Best wishes class. This is Physics 103, Lecture 3, which is 1C. So let's start by telling you that this lecture will be devoted to fundamental theorems of vector calculus. These are three essential tools of vector calculus. We have already done, and what will be our motive? Motive would be understanding the meaning and usefulness of fundamental theorems. Then this constitutes an essential toolbox required to study fields, which could be scalar or vector. And there is a running theme in all these theorems. The running theme is, if you sum of appropriate differentials, that is, you integrate the appropriate differentials, then you can find out about the function at the boundary. And this comes in three different forms: the gradient theorem, the divergence theorem, and the Stokes theorem, corresponding to each kind of differential that we studied in the last lecture. And of course, they involve line integrals, surface integrals, and volume integrals. So one of the advice that I would like to give you, that at this stage of the course, you should practice use of these theorems in all three coordinate systems equally well. The meaning and power, or even definition, of vector operations truly emerge through these theorems. In the last lecture, we considered del as an operator. Let me just remind you that in Cartesian coordinate, the del operator looks like this. And we know that it's not a vector, but it's vector-like since it operates on components. It's hungry to operate on something. It derives its meaning only from its action in different avatars. In gradient, it acts on a scalar to produce a vector field of maximum directed slopes. In divergence, it acts on a vector field to produce a scalar field of its source or sinks. In curl, it acts on a vector field to produce a vector field which are sources of vertex. This just as a reminder. The fundamental theorem of integral calculus is what we're going to discuss. We'll try to assimilate their meaning and use. That will be enough for physics in this course. We'll not try and prove them as you would do in a maths course. Physicists use lots of implicit assumptions till the math starts giving unphysical results. Then they sit down and take note of the purity of the conditions of mathematical theorems. But mostly the functions that we deal with are physical, and hence they will be assumed to be well behaved, and the domains on which they act as uncomplicated. So at this stage, let me get back to my notebook, okay, and okay, so what is the integrals in a vector calculus? It is, in the simplest form, okay, we can say that it is, suppose I have an integral df by dx, that is, so this is nothing but slope of a function, of a one-dimensional function from a to b. Okay, this is, I'm sure you know this, this is the function's value at the endpoint b minus f of a. In geometrical terms, if I say that I have a function, okay, f as a function of x, this is some arbitrary function, and then what I do is integration, meaning at each point I find out the slope, okay, and then I sum up the slopes, then it's if this point is A and this point is B, okay, if I sum up the slopes, then the result would be only dependent on the function's value at the edge or the boundary. Or even give a simple example. All right, suppose I have a function something like, let's say, this and then this and then this, let's say. Okay, so there are three different slopes. This is, let's say, A, B, C and D points, and they have equal intervals. Okay, so if I sum up the slopes, the sum of the slopes, so that would be FB minus f of A by, let's say, each one is delta x, the same thing that I've said. Then this will be FC minus f of B by delta x plus f of D minus f of C by delta x. So that is, you can see that the slopes cancels, that is FB will cancel with FB, FC will cancel with FC, and finally what you will be left with is nothing but the FD minus f of A by delta x. And hence, if I now say that instead of slopes, if I say slopes integral dx, then that is nothing but this is A and this is D, so f of D minus f of A. So this is extremely fundamental to the use of integral calculus. Now, in vector calculus, we have seen that we have three different kinds of differentials in findings. Okay, let's take now the gradient theorem. Okay, gradient theorem says that given a scalar field T, if we take the gradient of T dot dl along a curved path and integrate it, then it is nothing but the difference between the value of the scalar function at the two edge points. We know the physical meaning of gradient dot dl. This is nothing but the slope in the direction of dl. We have discussed that in the last class. So if I consider in a three dimension x, y, z, there is some arbitrary vector function, a scalar function, and the gradient I have already calculated. And then I can find out the grad t dot dl, and then so grad t dot dl along these lines, and then sum it over. Then it will become this. Since it depends only on the edge points, it really does not matter which path that I take. So it will still be the same. And hence, there is an important corollary. It's simple to state and understand, but it's very important in its implication that the gradient is always path independent. And the grad t is always conservative, that is. And if it is the same, then the A and B are the same, then of course it's a closed curve, it will be 0. Obviously the edges are at the same points. There are two important corollaries. All these three mean the same thing. We'll state it again. But note that the structure of this theorem is the same, that gradient is the relevant differential, and if I integrate it over the path, then it gives me the value of the function at its border. Here there are 2 points. Okay, now let's take an example. I'll take a simple example in, let's say, the Cartesian system, just to, and then this is the scalar function that is given, that is t, x square is just a scalar function in Cartesian coordinates, and the path is, let's say, the path given is path C, which is the, there is, let's say this is 1 and this is 1 in this direction, and there is a parabola, okay, so this, and so this is a parabola going to 1 1 1, okay, so this is 1 1 1, okay, and this is 1 1, okay, this is 1 1 0, and this is parabola, which means this is really z is equal to x square and x is equal to y is the path. So from this we also know that dz is 2x and dx is dy. So path C is the parabola given here. Now we have to prove the gradient theorem in this case. So first thing, of course, is to, let's say this is simple in terms of the left hand side of the, let me write down the gradient theorem again. The gradient theorem is grad of t dot dl over the path C is t b minus t a. Now this is, of course, a is 0 here, so everything is 0. So only thing we have to calculate is TB. So RHS is simple to the right hand side of the theorem is, of the equation, is easy to find out. This is T at 1 1 1 minus T 0 0 0, which is nothing but 1 plus 4 5 plus 2 7. Okay, so that is RHS. Now to find out the left hand side, okay, first you have to calculate grad t. So grad t is easy to calculate. This is, of course, 2 del by, you remember, let me write down for, okay, so this will be del t by del x I plus del t by del y j plus del t by del z k. Now let's do it. This can be simple enough that you can do mentally. So del t by del x is, of course, the first term gives you 2x, second term gives you 4y, third term is 0. So del 2x by 4y. Then first term gives you 0, second term gives you 4x, and third term gives you 2z cube. This is j. And then del t by del k, k term is only there in the third term. This is 2y 3z square k. Okay, so this is the grad t. All right, and what we already know, dl. What is dl? In this is Cartesian coordinate system. So dl is dxi plus dyj plus dzk, and the path restrictions come from this. Okay, and hence we can calculate del t del l. So integral of grad t dot dl over the curve that we are given. So this I can write down as simply, let's say, 2x plus 4x, that is the first term. I have replaced y is equal to x also. Then this will be 4x plus 2x, that x6, and plus 6x x cube 2x, and this is over, so 2 dz dx. So in the last I have used the fact that is dz is 2x. Okay, and everything is in dz is 2x dx. Okay, and this is simple because now it is everything is in x, and this is between 0 and 1, and that is simple to calculate. Okay, and that turns out to be 0 to 1, 0 to 1, 10x plus 14x6 dx, which is equal to, well, 5x square plus 2x to the power 7, 0 to 1, which is again 7. So this is same as the one that we calculated, and hence the gradient theorem is proven. The next fundamental theorem that we are going to describe is called the divergence theorem. So if we are given a vector function v, then the divergence, of course, is, now what does physically, remind you, what does physically divergence mean? This tells you where are the sources of the flux for V, lines of, so sources, like suppose it's water, then it's a tap, or it's a drain, sources or sinks. Okay, so if anywhere in the domain there are sources of V, okay, it could be field lines like in electricity, or there'll be water flow, okay, then it maps out at each point whether there is a source or not, and what is the strength of the source. That is divergence of V. Now, the divergence theorem says that if you take integral over any particular volume of the divergence of V and integrate it over the volume, then you can, so this is the total water or the field lines being produced or destroyed within the volume by looking at the source or the sinks. This should be equal to there is a surface for that volume, that surface S, and what is V dot dA. So basically what one is saying is, this is sum of, within the volume, this is sum of sources or sinks of V, sinks of the vector function, lines of force or velocity function, sinks within the volume, and this must be equal to the flux of the vector function V going through the surface. So whether you go to each tap and find out the water being water being added or taken away, that must be equal to the, or you can go to the border, to the edge, to the boundary, and just measure the, so in geometrical terms, okay, this will be, let's say, if we have a volume, an arbitrary volume, and there are, let's say, sources, okay, and there are, let's say, sinks where it is going away. So let's say there are sources and sinks, there are like taps, water taps adding water, or the drains that is taking, and or drainage that is taking water out. These are sinks I'm representing. Then this you can add up. This is equivalent to what is it? That all the vector, if you take any surface area A, any surface small area A, and integrate over all the surface integrals, that is either the vector function going out or so the flux. Okay, so this is a simple idea. Okay. The total added or being destroyed within the volume is same as how much of water is going out at the interface. Okay, and let's take an example of, I think it will become clear once you do an example. Okay, so of this idea, let me take an example with spherical coordinate system just to get you familiar. So example, let's say this will be 1, C, 2. This is example of divergence theorem. And I have chosen this example to be in spherical coordinates. Spherical. Okay, you can do it in any coordinate system, but each problem has its own symmetry and should be. So what is given is really V is R cos theta R hat plus R sin theta theta hat plus R sin theta cos phi phi hat. This is a given vector function, and of course corresponding to prove divergence theorem, okay, I need to give a volume such that I can identify the volume and the surface. So let's look at the volume and surface given. This is, let's take the volume to be a hemisphere of, let's say, this is a hemisphere volume, flat wave, and this is the hemisphere of radius r. Let's say this is x, y, or z, and this is radius r. Okay, so that's the volume. So this is the vector function, and that's the volume, and there's the surface. Now for RHS, we know that for RHS we require to find out the divergence of V. So let's find out the divergence of V. First thing is to do divergence of V for the left hand side, and divergence of V is given by, in spherical coordinate system you can obtain it. You can just look up these formulae, or normally will be given, but I'll tell you when I don't even try to commit to memory, I always get it. So this is r square r cos theta. This is the first term. Then the second term is 1 by r sin theta. Then there's a delta by delta theta. There's a wet factor. and the weight factor is, in this case, it is sine theta r sine theta, and plus the last term again the r sine theta del by del phi, and this is, now there is no weight, there is only r sine theta cos theta. All right, so these are the vectors. These are, of course, the vector function here, right? From here, from the vector function. Okay, these are the weight. Now, you can remember this formally, or as I told you, let me at this point point out that you could always remember the general formula for any, let's say, delta A. This I'm writing down the general formulae. This is easy to remember. F, G, H are the weight factors, right? And this will be del by del U, GH, A, U, where what is U? U in this case will be R. It could be, okay. And then this is in, I'm writing this in coordinate independent form. This is del by del V, F, H, AV plus del by del W, F, G, A, W. Okay. So in this spherical coordinate system, what is your F? F is of course 1, G is R, and H is R sine theta. Okay. And what is U? U is R, V is theta, and W is phi. They are the variables. So these are the weight factors, F, G, H, and these are the corresponding variables. So you can plug this in and obtain the this formulae. All right. For example, let's work that out. Okay. So this will be 1 by r square sine theta. So this will be delta by delta r. And what is G? G is R and H is R sine theta. So here also it is R square sine theta AR is the first term. Then the next term is del by del theta, and F is 1, H is R sine theta, so this is R sine theta, and this will be A theta plus del by del phi. F is 1, G is R, so simply R A phi. However, you can simplify this because sine theta has no dependence on R, so you can take R out. So this multiplication, the first term becomes really 1 by R square del by del R square AR. I'm just cancelling out this sine theta and this sine theta because this sine theta will not have any partial differentiation with AR. This becomes first term. And then R square sine theta is here. So sine theta I cannot take out, but R I can take out. So this will become 1 R sine theta del by del theta sine theta A theta plus 1, this R can come out because that does not depend on phi. So that becomes 1 by R sine theta del by del phi a phi. So what I've done is I've told you, even if you don't have with you if you remember how to write out a DL in any coordinate system, you can even write down all right. Okay, so this is just a reference of how we need to use a formulae. Quite often it will be given. You can always read it off. Okay, but it's good to be familiar with how to do it. Now, so now let me just calculate back. So apply the formula. So that becomes 1 by r square 3r square cos theta, the first term, then 1 by r sin theta, r 2 sin theta cos theta, plus 1 by sin theta, r sin theta, minus sin phi. Okay, so that on simplifying becomes 3 cos theta plus 2 cos theta minus sin phi. Okay, or I can write down this as 5 cos theta minus sin phi. So which means, okay, so I can write down this as my delta V. Okay, now I have to calculate the left hand side, that by doing now evaluating the tau, and so this is now 5 cos theta minus sin phi, and what is my d tau? D tau, of course, is r square sin theta d theta d phi dr. Okay, so this I can evaluate now. So 0 to r square dr, this is, I can take out this r and this dr, and that varies from 0 to r. Then theta will vary from 0 to pi by 2, because I am considering only the hemisphere. All right, so remember that we are only doing it for a hemisphere. Okay, and hence it's 0 to pi by 2, and the inside one, let me write down in terms of 0 to 2 pi. 0 to 2 pi, this is 5 cos theta minus sin phi d phi, and then sin theta d theta. So the whole integral turns out to be only that. Okay, this is, so the first term, of course, becomes r cube by 3, no problem. Then I evaluate this to be the first term, 5 cos theta sin theta, so that is cos theta sin theta I have to write down, but 2 pi minus sin phi d phi, that will give me 0. So but 5 cos theta d phi, that will give me Okay, so now it is easy to simplify to this. It is easy to simplify this because this term goes to 0. This term goes to, this term will go to 0. So we have left with 5 cos theta sine theta d theta over d phi. So this simply 5 cos theta d phi will give you 10 pi, okay, and cos theta, and this will simply become half, and because of that, now we can say that we'll get r cube by 3 dot 10 pi, and this reduces to half. So this is simply 5 pi by 3 r cube. Let's keep that as the answer for our left-hand side of the equation. Now let's go into the RHS, the right-hand side of the equation, which is a surface integral. There's the flux V dot dA over the surface S. And remember, the surface is again, okay, the surface has two surfaces actually. One is the surface, let's say S1. There's the hemisphere and the flat bottom, S2. So flat, this is, let's say, flat bottom. And this is the hemisphere. Okay, so we have to, of course, we'll have to do it both ways in that. So the two spheres, so the two surfaces, so one is hemisphere, let's say S1, and let me do both calculations simultaneously. This is the flat bottom S2. Flat bottom S2. So first we need to do is to calculate in any of these. First you have to do for S1 what is dA, such that we can calculate V dot dA and then integrate. So what is dA? D is the hemisphere. So dA would be, of course, at the fixed r. This is, remember, this is the radius r. So it's r square sine theta d theta d phi, and any surface element on this sphere, what is the direction? Of course, is r hat. Okay, so and this is phi will go to 0 to phi. What does phi range from? 0 to 2 pi full, and theta ranges from 0 to pi by 2 because it's only half the sphere. All right, of course, r is equal to r. So, then what will be, so let's say calculate V dot dA here, that we can do that here itself. So the only term that really, since it is R, the only term that will survive in this dot product is the R hat term in the wave function, in the vector function. Okay, so that is R cos theta. So this is only R cos theta R. Okay, and remember that this is r sine theta is the theta term. Okay, so let's get back to our V dot dA. So that becomes just cos theta. So it becomes r square, and now r is equal to r. In this, r is equal to r, and hence r cos theta becomes r cos theta sine theta d theta and d phi. Okay, so it now it's simply an integral over S1. The surface S1 will be the integral. Now this integral is run from, okay, our cube is there, so theta, as we have already figured out, theta goes from 0 to pi by 2, and d phi goes to 0 to 2 pi. Okay, so this can be equal to here r cube. Let's take it down. So this is 0 to pi by 2 sine theta cos theta d theta, and 0 to 2 pi d phi. It is getting cramped here, so let me remove this first and let's complete this. Okay, so that is equal to, this is for the so this will give you half, and so this will be r cube dot this will give you a factor of half, and this will give you 2 pi, and hence this will be simply pi r cube. This is the pi r cube. So this we have done for the hemisphere. Now let's go to the other, that is the flat bottom. So flat bottom, which is S2. What will be for S2? What is dA? dA is simple. This is the flat. Okay. So in which direction is that pointing? In minus k direction, which is nothing but plus theta. So dA is a total flat, but anything will be pointing in plus theta direction or minus k direction. And this is that simple flat bottom, and hence it is easy to write down. This is r dr d phi. Okay, why? Because we have taken sine theta is here is sine pi by 2, and that is 1, and r changes from 0 to r, and phi changes from 0 to 2 pi. Okay, so that is how the flat bottom dA, and hence I'll be only picking up r sine theta. I'll be only picking up it is plus theta. So in the vector function, the theta component is only r sine theta, and therefore v dot dA in this case, v dot dA in this case simply becomes r sine theta. Okay, and then r dr d phi. Okay, the integral will be of the range that we have already figured out. R would be from 0 to r, and d phi will from 0 to 2 pi. Fortunately, r can be completely separated out, and that is 0 to r square dr, and 0 to 2 pi sine theta. Sine theta is pi. Okay, so 0 to 2 pi, it is d phi, and that would be equal to r cube by 3 dot 2 pi. So that is another. Okay, so total for both the RHS for both surfaces, then we had seen pi r cube plus 2 pi r cube by 3, and that is 5 pi by 3 r cube. Okay, so that is, and let's check what we had gotten earlier from this also we have gotten the same thing. So that checks. So let me take up a simple example, which is a little bit more physical and straightforward, of divergence theorem. So what is given to us is that F is a constant C and R vector. What is to be proven is the divergence theorem for the spherical shell with inner radius R1 and outer radius R2. That is, the source is really inside. We have to prove it for this. All right. So we let us restate our divergence theorem. That is, the divergence of F over the volume, given volume V, must be equal to the surface as F dot dA. I have deliberately chosen an example in which there is not one surface, but there are two distinct surfaces. Okay. So now let's first calculate for the left-hand side. For the left-hand side, we'll calculate divergence of F, which is really simple in this case because it's spherically symmetric. So we should do this in the spherical polar coordinates, and there is only AR. There is no A theta. There is no F theta or F phi. So the first term in spherically symmetric is, of course, 1 by R square del by del R square, and FR term. That is the first term. So in this case, it is 1 by R square del by del R square, and FR is CR. So this becomes 1 by R square and R cube. So C3R square, R square cancels. So this is really 3C. So the divergence is 3C. Now it is to be able to integrate divergence. It is quite simple over the volume. We don't have to do much because we know it is spherical over the volume d tau. So this is a constant, and hence it is simply 3C, and I can directly write down without even integration that this will be 4 pi by 3 R2 cube minus 4 pi by 3 R1 cube, because that is simply the volume, which you can calculate if you want to integrate over R theta and phi, and that becomes 4 pi C R2 cube minus R1 cube. Now what I wanted to illustrate really is the RHS, the surface. Okay, so now for this, over the surface, F dot dA, but now there are two surfaces, and hence we can write down as S F dot, let's say, dA1 plus F dot dA2 S2. Now the question is, what is dA1 and what is dA2? Now let's write down what is dA1. dA1 is the inner. Go back and look at this. So dA1 would be having the R in this direction. The normal would be in this direction, and hence dA1 would really be R1 square sine theta d theta d phi. But what is the direction? Direction is minus R. What about dA2? dA2 would be R2 square sine theta d theta d phi, but it will be in plus R direction. That's the difference. Okay, so now we can, the first integral, of course, the F is given as C R hat. So on the surface R1, this is nothing but R1 hat, you can see. Or it is better to write down in terms of C R1 R hat, that is the, and dA is R1 square sine theta d theta d phi r hat. Now this is minus r, that's the point. Okay, so this and this are the only two vector components. So this and the other one, of course, so this is surface S1. So this is surface S2 would be similar. This will be R2 R hat dot R2 square sine theta d theta d phi plus r. And now we would be, this is, and this will be dotted. So they are exactly similar, and we know the what this will turn out to be. Okay, so this is just the surface integral. So this is C R1 cube can be taken out, and then this is simply sine theta, this is minus, because minus, first one, sine theta d theta d phi. Of course, d phi is changing from, theta is changing from 0 to pi, and this is 0 to 2 pi, and plus similarly C R2 cube and a similar integral sine theta d theta d phi 0 to pi and 0 to 2 pi. Each one of these integrals will give you 4 pi, and hence this is indeed the answer. So this is the same. So this is the same as what we have gotten from here. The point that I wanted to illustrate was how to treat two surfaces and choosing the correct normal. Okay, in this case, the normal were in pointing out. Okay, while treating the surface, and the inside was pointing to. This is actually a physical example, which you will see it in the next chapter as well.